How's it going, everyone? So we're going to wrap up the lecture on the area between curves. So last time we were doing kind of the most simple case, I guess, area between the curves. Now let's get something more complicated. It's because in our example, well, one function was always on top of the other one. So we had a clear, like, one function, we had like y top, and then we had the other function y bottom. So it was very clear what the top and bottom functions were. So we knew how to handle this scenario. But what happens, let's say, now if, one function kind of takes over the other one as the top or the bottom one. So let's say something like this happens. For example, maybe this finishes there. So something like this. Now, in different regions, one function is the top one and the other function is the bottom one. So like, for example, the three different regions we'll get will be, the one between, so like this region, and this one. So we have three different regions in this case. And the formula is still the same. It's still y top minus y bottom. It's just what is the top function and what is the bottom function changes. And so let me do an example here so that it's it's clear what to do now. So all you have to do is figure out which one is the top, which one's the bottom. That's kind of like the only technical issue here. So let's take an example. Let's take, suppose we want to find, let's say one function is this. So we want the region bounded by, and we want the area of this region. The region bounded by y equals sine x, y equals cosine x equals 0, and x equals pi over 2. Okay, so we want the area of the region given by the curves or that are bounded, that are given by these guys. So again, since we're only going from 0 to pi over 2, we don't have to draw negative numbers. So here's 0, and then let's say here we put pi over 2 at the end. So x equals 0 is this, vertical line. X equals 0. And x equals pi over 2 is this vertical line. Remember, y equals a number is a horizontal line. X equals number is a vertical line. So these will be our boundaries here. And then next we need to see the one that sine and cosine create. So let's maybe put like a intermediate point here is like pi over 4. And if you remember, this is exactly where sine and cosine cross. Remember, the very first thing you want to do is to see where these functions cross each other. So, if you would set sine x equals cosine x to see where these two functions cross each other, as we did in the last examples, you'd have to figure out some angle x between 0 and pi over 2 where these cross, if there is any. And either you remember from trig, like geometrically, why that point is pi over 4, or another way of doing it is you can think, if you divide both sides by like cosine, for example, then you would get sine over cosine, which is tangent, and then this is just 1. So this is also the angle x in which the tangent of that angle is 1, which again you might remember from trig is pi over 4, Or if you don't, x would be the tangent inverse of 1, which that is 45 degrees or pi over 4. So this is pi over 4. So there are many ways to get this, but long story short, this is the point where the two functions intersect, sine and cosine. And at pi over 4, they both have a value of root 2 over 2. So you remember sine of pi over 4 equals the cosine of pi over 4, and that's root 2 over 2. Which is approximately 0.7 or so. So maybe let's put like 1 up here. Root 2 over 2 would be somewhere like here. Okay, and then, so cosine we'll put in red, let's say. So let's say y equals cosine is red. Let's put sine in blue. Okay, so remember cosine starts out at 1, and then it'll hit root 2 over 2 at pi over 4, and then it hits 0 by the time it gets to pi over 2. So it'll look something like this. And then pi is the exact opposite. It starts out at 0, sine x, and then at pi over 4 it hits the common point root 2 over 2, and then at pi over 2 it hits the maximum value of 1. So sine looks like this. And now you can see that we're getting two different regions where what's y top and what's y bottom are different functions. So maybe we'll call this one R1 for region 1, and we'll call this one R2 for region 2. So the idea is pretty straightforward. You just add up these two areas. So we're going to have to use two different integrals to get this. And in each case, what's y top and what's y bottom is different. So the area that we're interested in, if I erase this, might as well do that. The area that we're interested in now is the sum of these two, and it'll be equal to this. So the area, which we'll maybe call A is region 1 plus region 2, is given by, okay, region 1, the area, is going to be from 0 to pi over 4, right? 0 to pi over 4 on the x-axis. And then y top, which in this case is cosine, minus y bottom, which in this case is sine. Okay, that's region 1. And then plus, from pi over 4 to pi over 2 now, the second half, and now switch it. Y top is sine, and y bottom is cosine. So that's going to be how we find the area between here. So it's the same concept, you just kind of break it down into two separate regions. Okay. So now all we have to do is a little bit of calculus. So if you recall, what are the antiderivatives of these two? So the integral of cosine was just sine. So this becomes sine x. And maybe let me put this like in colors. So we're tackling this one first. This is sine x. So the integral of cosine is sine. And then minus negative cosine x. Remember, this is the integral of sine, because just the derivative of negative cosine gives you sine back, and then this minus sign just comes along. So overall you have minus negative, which will just be plus. So this is plus cosine x. So that's the antiderivative And then again, we're going to evaluate that from 0 to pi over 4. Okay, so we have this. That's the blue piece. And then plus, and then the red piece here. Similar idea is this antiderivative is negative cosine x, and then this is a minus sine x. Because ignore the minus sign, that just comes along. The antiderivative of cosine is sine. Okay? And then again, if you always want to double check, the derivative of this should give back the integrand. So if you take this derivative, this negative cosine becomes a sine, and this minus sign becomes a minus cosine. So yes, you do get what you need. And then we're going to evaluate this from pi over 4 to pi over 2. And this is the red piece. Okay, so then this is going to be the sine of pi over 4 plus the cosine of pi over 4. That's what happens when we stick this guy in there. And then all of this minus the sine of 0 plus cosine of 0. But again, this needs parentheses here. Alright, because this expression is not just a single quantity. It's two quantities being added to each other. So when we take the minus, when we take capital F of B minus capital F of A, all of this whole thing is capital F. So you stick 0 into it, which is A in this case, and that whole number, whatever you get, you take the minus of that. So you have to be very careful that we put a minus in front of the whole quantity here. Okay? And then this itself, you could chunk off if you want, but you don't have to. It's basically the associative property of addition. I mean, that's fancy words, but at this point, we've done all the things, the careful things we need to do. Okay, and then to make our lives easier, well, okay, never mind. We'll just go with this. So then plus, and then now you're going to say, stick pi over 2 in for these. So plus negative cosine of pi over 2 minus sine of pi over 2. Okay. And then minus, again, you want to put parentheses, negative cosine of pi over 4 minus sine of pi over 4. Okay. So then maybe we'll come back up here. Alright, so as we talked about, each of these is root 2 over 2. So we have root 2 over 2 plus root 2 over 2. And then sine of 0 is 0 and cosine of 0 is 1. So overall this is a 1, and you put a minus sign, so this is a minus 1. And then cosine of pi over 2 is 0, and the sine of pi over 2 is 1. So overall this gives another minus 1. And then notice here that both of these have a minus sign. So we could factor out this minus sign to make this a plus essentially. But maybe let me just leave it this way. So this is again minus now. Each of these is root 2 over 2, but with a minus sign is negative root 2 over 2. So minus root 2 over 2 minus root 2 over 2. Okay. And then now, if you add anything to itself, it's twice that thing, right? X plus x is 2x. So when you add these two to itself, you just get 2 times root 2 over 2 which the 2 just cancels and you get root 2. So this is just root 2. And then these two give a minus 2. And then this, again, is a negative root 2. But with that minus sign gives you plus root 2. So overall, we're getting 2 root 2 minus 2. And that is the final answer. Okay. So yeah, again, you have to be really careful when you're doing this last step where you're plugging in the endpoints and stuff like that. But hopefully, if this makes sense on how you can be very cautious to make sure this works. Okay. Now, next up, we want to look at an example that is not so easily done in the framework that we've developed, but can be done a lot easier in another way. So that sounds really vague, so let me explain. So suppose we have, one parabola, let's say, sideways parabola like this, that opens up like that. And then you have another sideways parabola that maybe opens up like this. And you want to find this region. Okay. Now, there is no clear y top or y bottom in this case. Like, you may think this is y top, but if you go down here, it's actually y bottom compared to this. So in this half, this is y top, that's y bottom. But down here, this is y top and that's y bottom. So it's kind of tricky and really hard to deal with if we just consider functions like in the form y equals something. Because normally, what do we do when we have a function? We say, okay, like y, or which is f of x, equals like x cubed. Meaning that if I hand you an x coordinate, this function tells you what the y coordinate should be. So if I give you 1, on this graph you know that you need to go to a 1 cubed, which is just 1. And that's where you put your dot. It tells you where to go on the y-axis. If I give you 2, it tells you to go to 2 cubed, which is 8. So normally the way that we write things in the form y equals, we're getting a y value. But what if you do this in the opposite way? So what if you consider instead a function in the form x equals some function of y. So now I give you the y coordinate, and this function gives you the x coordinate, where to put on the x-axis. So for example, let's say, I don't know, let's say y squared, or root y, for example. So notice that if x equals root y, and you square both sides, you get that x squared equals y. Meaning that this thing should basically be the graph of a parabola, essentially. But let's pick a few points and see. Okay, so in a sense you may say, well, can't you do this for almost every equation? And the answer is basically yes. If you can write something explicitly like y equals, usually you can just solve to turn it into x equals something. So yes, it's just kind of more familiar to do it in the first way, y equals something. But so if y is 1, this tells you that your x coordinate should be the square root of 1, which is just 1. So you put a dot here. So yeah, g of 1 is 1. Now if y is 4, so what is g of 4? It's root 4, which is 2. So it's saying at y is 4, you should be 2 units out. You should be at the square root of 4, which is 2. So you should put a dot here. And notice that, yes, this does make a parabola. If you keep doing this, these are the exact coordinates of a parabola, 1, 1, 2, 4. Because 1 squared is 1, 2 squared is 4. So it's the same thing, it's just kind of different pieces of information. One tells you the y coordinate, how high or low to go. The other tells you the x coordinate, how left or right to go. So it's the same thing. And the advantage of dealing with functions in this form is x equals some g of y, is it is very clear in this context what we can do. Say the analog is, you know, we had y top and y bottom. This is like x right, or x of r, and this is x left, or x sub L for short. Now, through basically a very similar strategy, we can see that, you know, what is one like rectangle? Remember, we always approximate the area with rectangles. What would one of these rectangles look like? Well, you know, if I pick this point here, I take this and I take that, this will be kind of like the base, in a sense, of the you can think of it as base or the height, it's kind of up to you, but it's one of the dimensions of the rectangle. And then you're going to make the rectangle, you know, have a certain width. And the width, instead of being a delta x, is, notice that it goes in the y direction. It's not a left and right thing, it's an up and down thing. So this is actually a delta y. So maybe let me erase some room. This is a delta y. So now, like, this is delta y, and how big is this? That is xr minus xl. This distance here, from here to here, that's exactly xr minus xl. So you take the right function minus the left function. And so now it's very quick to see what the area becomes. The area now is the integral. You can say a to b again, except now a to b, these are things on the y-axis. So this would be like a, and this would be b. So points on the y-axis, not on the x-axis anymore. So it would be something on the y-axis, and instead of being a f of x, a function of x, they're not functions of x anymore. So it's going to be x right minus x left, instead of y top minus y bottom. And then instead of dx, it's a dy. So because we're going up and down, dx, which was a left and right thing, gets changed to delta y. And these functions, instead of being y equals functions, they're functions of the form x equals something. So this is the area that we'll use, like, for this scenario. Okay, and let's do an example. So find area y equals x minus 1. Okay. Okay, so this is the equation of a line, which we can rewrite this, you know, as I was saying, you can rewrite this in the form x equals something, right? If you just add 1 to both sides, this is the same as y plus 1 equals x. So this is now, if I give you the y coordinate and you add 1 to it, that tells you what the x coordinate should be. So this is a function of y. And then here, this is a little more tricky, not too much more, but you know, if you subtract 6 from both sides and divide by 2, well, let's say, so you subtract 6, you get this, and then divide by 2, you know, that means divide this by 2 and divide that by 2. So then this is the same as 1/2 y squared minus 3 equals x. So now we have, again, if you hand me a y coordinate, you can give me the corresponding x value. Okay. So these are, they'll tell you the same curve, it's just, you know, more convenient in this case. Okay, and then the next thing is, remember we always found where these things intersected. You always wanted to find where these guys intersect. Okay, and you know, there's many ways to do this. You can square this to turn it into y squared, and then set both of these equal. So what I mean by that, or would it be easier, or maybe that's one option, or the other option is, since both of these equal x, what you can do is just set each of these two equal to each other. So you can take y plus 1 equals 1/2 y squared minus 3. Since we want to find the point, you know, whatever these curves are, maybe it's not going to look exactly like this, but you know, at these intersection points, the value x is the same, and so is the value y. So we can safely say that at this value x, these two things are the same. Whatever that y is, we're going to solve for that. Okay, and so this basically is a quadratic equation. If you want to make it easier, we can multiply both sides by 2. So then we get 2y plus 2 is y squared minus 6, and then move everything over to one side. So that we have y squared, and then minus 2y, and then minus 8 equals 0. Okay. And then this will factor, if I come here, this factors into the following, or sorry, this should be plus. Okay, so this factors into that, and so we get that y equals -2 and 4. Those are the values where these curves intersect. The y value anyways. Oh, maybe. So this is the y value. So what is the common x value? Well, you can stick these y values into either of these functions because the functions have the same x and y coordinate at that point because they're intersecting. So might as well do it at the easier one. So what we get is that x at -2, right? X is a function of y, but maybe I shouldn't be more confusing. So if you stick -2 in, you will get into this guy. -2 plus 1 equals x, and so this is -1. So we know that one intersection point is x is -1 and y is -2. So that's one intersection point. And then the other one is, if you stick 4 into here, you get 5, right? So then you get x is 5 and y was 4. So these are the intersection points. Which we'll need. Okay, and then now to graph these. So again, this function is pretty straightforward to graph, not too bad, because it's just a line, right? And we know two particular points that we really care about. So we'll only go as far as -1 on the x-axis because that's one intersection point. So let's call this, like, let's say -1. Let me make this longer. So at -1 we're here. Now what happens when we stick, we can do either function here. It's pretty, these two are very straightforward. The difference between these two is a little larger. But if you stick -1 into this guy, you get -2. So we have a point down here. And then you stick 0 into here, you get -1. And then stick 1 in, you get 0. Stick 2 in, it just keeps going up, right? So when you stick 2 in, you get 1. And so on. And we'll go until 5 on the x-axis. Okay, so these were the two intersection points, and this should look something like a line, hopefully. And put this more down. Okay, so this is what we have. That's one of the functions. Maybe I should have done that in red, but too late now. So this says y plus 1 equals x. And then you want to do the same thing with this guy here. Now this one's a little trickier to deal with, but you can pick either one here. So now if I give you a certain y coordinate, you can tell me what the x coordinate is. So let's look at this guy. So if you stick 0 into this guy, for example, what do you get? You get -3. So at y is 0, the x coordinate is -3. So we're down here. And then if you stick, for example, 1 into here, you're going to get 1/2 1 squared minus 3. So what is that? 1/2 minus 3, which is -2.5. So then now, oh sorry, I plotted this at the wrong place, my bad. Let's go back 1 second. So if you stick y as 0 in here, we got negative 3, right? So 1/2 0 squared minus 3 equals x. So x is negative 3. So I put it on the y-axis, again, bad habit because I'm used to this. But we need to go to negative 3 on the x-axis. So we need to put our dot. Y is 0, x is negative 3. Our dot goes here, actually. And then at 1, we were at negative 2.5. So when y is 1, we go to negative 2.5. So we're here. And then notice that that will be the same thing for negative 1, right? If you square 1 and negative 1, you get the same thing. So 1/2 negative 1 squared minus 3 is also negative 2.5. So when y is negative 1, we're also going to be at negative 2.5 on the x-axis. And then maybe let's do y equals 2. So again, plus and minus 2 are going to give you the same thing. So 1/2 2 squared minus 3 is going to be 4 over 2 minus 3, which is 1. Or sorry, negative 1. So then now at y is 2 or negative 2, the x value is negative 1. So at 2 we're at negative 1. And also at negative 2 we're at negative 1, which we knew that because that's the intersection point. Okay, and maybe you can kind of see now that an equation of this form is just a sideways parabola, right? When y was equal, like, if we had y equals 1/2 x squared minus 3, this was a parabola. So when we switch the coordinates, it's not too far-fetched to see that this now just becomes another parabola just shifted, like it's rotated a little bit. Okay, so then this becomes a rotated parabola. And then this, will keep going down like this. And then this will continue on like that. So we'll continue on until we hit this intersection point. Okay? And so we're now interested in the area of this region here. And so I can erase this. Just know it keeps going on, but now notice that this is a perfect x right minus x left scenario here. So this guy here, the line is x right, and the sideways parabola is x left. Okay, does this make sense? This is the one on the right, this is the one on the left. Okay, and so now we can find this area more straightforwardly. So it's going to be the same equation. Now the area is, again, the area of the region is the integral. Now remember, we're not going to go on the intersection points of the x-axis, but rather the y-axis. So we're going to go from negative 2 to 4. Those are the y coordinates. Very important. Notice this distinction. These are y coordinates. Because we're not doing dx. We're not going left to right. We're going up and down. So our limits of integration are along the y-axis. And then we take x right, which is y plus 1, minus x left, which is this, and then this is a dy instead of a dx. So overall, This is from negative 2 to 4 of negative 1/2 y squared. Then this minus hits that guy to be a positive 3, and that combines with that to be a 4. And then the y is just hanging out. Okay. So see, now we have everything in terms of y, which is fine. Remember I said if this is a y, or a z, or a w, or r, it doesn't matter. The integral here is the exact same way. There's no difference at this point with what we're doing. Okay. So then, if we work out the antiderivative, I'll leave the evaluation for you guys, but just to show you it doesn't matter whether we use x or not, or y. Right, this antiderivative, or integral, is, remember, we ignore the negative 1/2. You just say it's negative 1/2 times whatever the antiderivative of this guy is, which is 1/3 y cubed. So overall, the negative 1/2 times the 1/3 is a negative 1/6. So this is negative 1/6 y cubed, and then this is a 1/2 y squared, and then the last one gives us a 4y. And again, if you don't believe this, take its derivative. If you take the derivative of this, you will get exactly the integrand back, this thing here. And then we just evaluate that from negative 2 to 4. And once you do all this arithmetic, apparently this just gives you 18. So that is the final answer. Okay, so yeah, sometimes it's much more convenient to do x right minus x left. There is a way to do this with y top and y bottom, except it will require 2 parts. So it's a lot easier to just do it this way, and you should be able to like get familiar and comfortable with, switching, whether you have a function that gives you the y coordinate or it gives you the x coordinate. It'll be valuable to learn this skill anyway, so this is a good start. Okay, next, we can start with the next section. Definitely won't finish it, but this is kind of going to be the first application that we do of the integral. So we're going to be able to apply the concept and the technique of like the Riemann sums and the integral to come up with the volume of very like elaborate shapes, or shapes that we already knew of. And if you ever wondered, how'd you get this volume? Okay, so this is section 5.2 and it's just called volume, so nice and short title. So maybe let's start with just something very basic. Something we'll get more complicated later. So, if you have, when you have a bunch of crackers and they're in their little bag, each cracker is like a small piece of like an overall cylinder, right? So you have like, let's say 20 crackers, and that all comes together to form this big cylinder. So you have a cylinder, and let's say we just focus on one of the crackers within the cylinder. So we're just looking at maybe one of the crackers in there. Now, each of the crackers has some thickness, right? It may be like really thin, but it does have a thickness associated to it. So it has some thickness like delta x. So that's like how thick the cracker is. And then that cracker also has an area. Its surface, the top of the cracker, encompasses some area. So this is like some area that it has. So this is area. Okay? And we could think of putting this thing, you know, on a coordinate system so that you know, like this is like 0, and you know, we keep numbering things, and this is just some point x sub I, this is some point x sub I plus 1, and so the thickness is delta x is x sub I plus 1 minus x sub I, and let's say we pick this very particular point. So I'll erase this guy. So instead of getting the area right at the top, let's say we take the area of this guy right here. The area formed by like this piece. It's all the same. It's still like a circular area. So but we're going to pick this point out in particular and say it's like x sub I star. Again, it's like a sample point. So you pick out the little circular area at that point here. So again, like if you think about it, that cracker, even though it's really thin, it could be made out of a bunch of really thin stuff too. And so you just pick one of the little thinner pieces that it's made out of and calculate its area. So this is the area at x sub I star. And you're just going to say that, you know, this is pretty representative of the area of the whole thing, which it is. You know, if our shape, which we'll look at a little later, let's say our shape isn't so uniform. Let's say it looks something like this. Then you could see like that the area of this little piece and this piece are different. One is larger than the other. But in this case, in the cylinder, all of the areas are more uniform. And so that's where, you know, saying, oh, this is the area at some point, let's say like 0.1 versus the area at 0.2. You know, the point, I mean like x1 star, xi star. These are different. So you want to be able to, in general, say that the area changes. In this case, this is nice, the area doesn't change, but we'll still use this notation to be as general as possible. Okay. And so, what is the idea here is the volume of the cylinder So the volume of the overall cylinder can be approximated by, if we add up, you know, the volume of each of the crackers within it. Each cracker, or a slab in general, is some slab of this guy. By adding up the volume of these slabs, or in this case, crackers. Oh, maybe I won't write that. So we have, you know, a bunch of different slabs. You know, this one here too. You know, this is another slab. So add this volume up, add that volume up. Add up all these volumes, and you should get an approximate volume for the cylinder. And then what is the volume of each of the slabs? So volume of each slab is, okay, in general, you know, the volume is just the area that the thing encompasses times the thickness, is what is the area times how thick it is. That'll tell you what the volume is. So the volume of each slab is the thickness, which is delta x, times the area. So it's the area at the specific point times the thickness, delta x. Okay? And you may already be like, hey, I know exactly where you're going with this, because this is exactly what we did with the Riemann sums. Very, very similar. So you guessed it, what happens when we take an infinite amount of slabs? If we let the number of slabs become very, very, very large, then we get basically the exact volume. So what I mean is the approximate volume is this. It's the sum of all the slabs each term in this sum is just the volume of the slab. So when I is 1, that's the volume of the first slab. When I is 2, that's the volume of the second slab. You're just adding up these volumes. So then actual volume is we let the number of slabs go to infinity. And remember, when we did this, instead of having this symbol here, the sigma turned into the integral sign, and we went from some point A to B, right? A to B. And then the area, this just becomes A of x dx. So the volume of any shape can be given by this formula. So if you have a formula for the area, which we'll see how it can change in a second, this is not, in our case, the area of each cross section is the same. Every single slab or cut is a cylinder, and that, is like basically like a small cylinder. And so each of those have the same area, or you can think of it being a circle, right? So, but we'll see a different thing. And then I use the word cross section. So a cross section is basically how you create like one of these slabs. So if you cut through anything with like a sheet of paper or like a plane, if you imagine passing a tiny sheet of paper through a surface, then the intersection of your surface with that piece of paper is what like a cross section is. So let me be a little more clear. So this is the idea of a cross section. So yeah, again, let's say I take a cylinder. Let's make it upright this time. And then I take a piece of paper, and like say that piece of paper, it can like cut through the cylinder. Right? The part that intersects with the piece of the paper is like a little circle, right? So each little piece, each little circle that you get when you cut it with a piece of paper, that's called a cross section. So a cross section is the intersection of your surface. So, and by surface, I mean like your object, like a sphere, a cylinder, a bowl, anything basically, with a plane. And by plane, I mean a piece of paper essentially. But the piece of paper can be oriented in any way. So, for example, the piece of paper can be like this, it can be like this, or it can be like that. You know, it can be flat like this, it could be like that. And so you can take different cross sections. So look at this mug here. We can cut it like this. So if I was able to pass this piece of paper through the cup, then those cross sections would be circles because they're going along this way when I cut this way. But I could also cut it like this. And then those cross sections would kind of be more rectangular, right? Because you can see that if you cut through this guy like sideways, you're gonna pick up like these like rectangular pieces here. So that's what a cross section is if you cut a surface, by surface I mean some kind of object, if you cut it with a plane, aka a piece of paper that you can orient in any way, the intersection of those is a cross section. So for example, if we cut a cylinder with like this, flat like that, the cross sections will be circles. Okay, but we'll get to that a little later. Or maybe this is a nice example. Let me get a nice prop. So if we have a sphere here and we cut it with sorry, my video cut out for a second, but we were talking about the sphere here. So actually this is a nice example because you could see, notice how this guy here, the middle circle, is a lot smaller than this top circle here. And these like circles are getting smaller and smaller and smaller till they get to the top. So you can see that the cross sections that we would get by having a plane cut through horizontally, they are circles, but these circles are getting smaller and smaller and smaller. And that's where, you know, the area is changing. So that's what it means by the area as a function of x. It's not something that stays constant. It could change. In a cylinder it doesn't, but like in the case of this sphere it will change. And so we'll get to that here in a second, and we'll calculate with this concept. We will calculate both the area of a cylinder and a sphere and more strange looking shapes. So let's start with the sphere, or sorry, the cylinder. We know that, you know, if we take the cylinder here, and you know, again, you can put this on some coordinate axis, and let's say you call this x. What is the area of this guy here? Well, what is the area of the cross section? I'm saying the area is pi r squared, where r is the radius of the cylinder here. And notice that this actually does not depend on the choice of x, which is good. That's what we were saying. No matter what x you pick, the cross section, the area of the cross section, or what's called the cross sectional area, does not change. And so this is going with our intuition. And so we get that the volume of the cylinder is going to be the integral from, okay, we can call this point A and this point B where it ends. This is the integral from A to B of pi r squared dx. Now notice that these are just constants, right? Pi is a constant, and in terms of the variable x, r is just some fixed number too. Like the radius is fixed. It never changes on the cylinder. And so this is just the same as you can pull these out as a constant. Okay? And so you can think of this being, there being an imaginary 1 here. There's a 1 or whatever. But either way, the integral here, the integral of just 1 is just x, right? Because what's the derivative of x? It's 1. So what we're getting is that this is pi r squared x evaluated from a to b. And then this is pi r squared b minus pi r squared a, which if you factor out the pi r squared is b minus a. Now what is b minus a though geometrically? B minus a is this length here. B minus a is actually just the height. It's the height of the cylinder. So we get that the volume of a cylinder is pi r squared h, which is, follows from, whenever you learn this. And the idea is very simple, is you know that each little slice or each little cracker has area pi r squared, and then you just add this up a bunch of times. And that is where the h is coming from. It requires a little bit of calculus to see that, but that's the concept. You add up the little volumes, each little cracker, add up those volumes, and they would sum to the overall volume. Okay, so that's pretty neat right there. And for time's sake, I think this is a good stopping point. So next time we can continue on to more stranger shapes and things like that. Okay, thank you.